In this video, we'll develop some standard measures of numerical error. After studying this video, you should be familiar with the following measures of numerical error: true error and true relative error, approximate error and approximate relative error, and a stopping criterion that's used for iterative approaches. We'll also want to know some background on when to use these different methods of error. Before we get into that, let's talk a little bit about sources of error in mathematical modeling. We can have several sources of error in mathematical modeling. One is the assumptions that we make in developing the underlying theory of our mathematical models. Another is uncertainty in the experimental data that underlies the model, perhaps data used to determine model parameters. A third source of error is approximations that are made in developing the numerical algorithms themselves. We'll look at this a lot in Engineering 240 for each method we look at. And a fourth source of error is errors caused by the limitations of the computer. As you may or may not know, computers store numbers with finite precision, and this does have some ramifications for numerical accuracy. We will talk about those implications in a later video as they become more relevant to the numerical techniques that we are studying. So let's get to those standard definitions of error. First of all, for quantifying error, we can define the true error, E sub t, as the true value minus the approximation. So the approximation will be generally the result of a numerical calculation. Now, the true error is an important number because it tells us the number of significant digits in our result. However, it's not always that useful because the magnitude is not relative to the solution itself. So for example, a true error of 0.1, for if the true value is 100, that's 0.1, that's 0.1% error. That is not too bad. However, if the true value is 1, that would be a 10% error. So we'd like to have some measure that gives us a meaning of the relative magnitude of that true error, and we get that from the true relative error, where we simply take the true error, ET, that's what's in the numerator here, and divide that by the true value. Now, one thing you might be wondering is, well, wait a minute, if this is a numerical methods class and we're using numerical methods to calculate approximations where we can't solve something exactly, then we may not know the true value. And that's generally the case. We generally do not know the true value. So we can use another measure of error called approximate error. And approximate error is defined as the present approximation, and this is again our numerical result, minus the previous approximation, and this is a numerical result. It's an application of the same algorithm with less precision. And we'll talk more about what that specifically means in the context of each numerical method where approximate error is a relative method. Now again, because approximate error doesn't give us a true sense of the magnitude of an error, it's much more common that we'll use approximate relative error, denoted by epsilon a, and that is given by the present approximation minus the previous approximation, all divided by the present approximation. So again, this is all based off the assumption, a key assumption here is that the present approximation is better than the previous. So we're basing this measure of error on the assumption that when we apply the same numerical algorithm with more precision, that gives us a better approximation. And this brings us to one of our main uses of approximate relative error, and that's in iterative techniques. For iterative numerical techniques, what we do is we repeat a calculation over and over with increasing precision until we reach a desired accuracy. That desired accuracy target is called a stopping criterion, or stopping tolerance. We usually would denote that by epsilon s. So we can say an iterative method converges when we've repeated that calculation to the point that the approximate relative error, the absolute value of the approximate relative error, is less than or equal to the stopping criterion. In other words, what we are doing is repeatedly calculating the approximation with increasing precision and recognizing that at a certain point the solution, even as we increase the precision, the solution is not changing all that much, at least not within the tolerance that we've set in our stopping criterion. And we'll see more concrete examples of how these different error measures apply throughout the course. But this video, we have them all in one place so we can refer back to these throughout the quarter.